Hello, and a very good morning to everyone joining us from North America, and a very good afternoon to fellow friends from EU and other parts of the world. I would like to welcome you all to our one-day Plastics in Electronics conference event organized by SPE and Young Professionals Committee. My name is Jimmy Shah, and I'm the Senior R&D Engineer at Impact Plastics and ICPG. I also serve as the Chair for Young Professionals Committee and the Technical Chair for today's conference. We have a great lineup of event and speakers for all throughout the day, starting from conductive polymers for wearables to modified polymers for electronics, and a deep dive in between for hybrid direct read processing. Just to give you a little bit more background about the conference, we have a total of 9 speakers throughout the day, including 2 keynotes, one for the morning session and one for the afternoon. Each presentation is about 20 minutes with 10 minutes of Q&A, with keynote presentation of about 45 minutes and 15 minutes of Q&A. Presentation will start at scheduled time, and so you can always catch up for your topic of interest at its time. Questions can be asked through the Q&A function in Zoom. Moderator will read the presentation questions to the presenter. There will be a 15-minute break time after each presentation, and during lunchtime we have our SPE favorites Lindsay and Mercedes interviewed Justina Sanchez from TUV. At the end, stay tuned because we always have the virtual cocktail hours, be it in physical or the virtual conference sessions. We will be doing it through the Remo platform. This is your final chance to catch up with your fellow attendees, so stay tuned.
So I'm talking here about these rolled capacitors where a capacitor film is coated with a metal such as aluminum. Then we have 2 rolls of these sort of like wound together to then generate your anode and cathode by putting on these end caps and making connections. So again, you'd make a connection to top here and to bottom here. Now, the relationship that would then be in place would be that the energy density is then directly related to the K, the dielectric constant, as well as the breakdown strength to the power squared. So again, a doubling of the dielectric constant, if you can keep the breakdown strength the same, would lead to a doubling of the energy density, and doubling of the breakdown strength, again, a constant K value would then result in a 4 times energy density. Now, the applications we're looking at for this would be the railgun, as well as systems like the emails, electromagnetic aircraft launch systems. You're also looking at things like the accelerator portion of the electronics for like vehicles. You'll also, as things like the electric hybrid jet come on board or start to come on board in the future, they could be looking for materials as well that may have higher temperature characteristics.
So why would we need to have electrical conductivity in plastics? I mean, you all know, and many of you know, that plastics are very good insulators. And actually, this is what the reason why they've been used in the early ages. It's a good feature. I mean, it's a very important feature of plastics. But in many cases, you want to overcome and to avoid this insulation property of plastics in many applications where you want to replace metals. Because you, thanks to I would say the advantages of plastics over metal in terms of conversion into complex shape, into the ease of processing, but also in terms of resistance to corrosion. The problem is that plastics being insulator, then you have the problem of electrical conductivity that you have naturally with metals. And this can be a problem in some cases.
So looking at the details of our process chain, what we've been trying to do is basically first develop a solution that we can print on an injection mold. So we're using with a hybrid dispensing system to create functional traces onto steel. And so because of that, we needed to study a coating that could be deposited in between the printed electronics and the steel to make sure that then they could be released effectively. And so we started looking at that. And so we started looking at how we can develop this coating, how we can effectively dispose that coating onto the surface before we're doing the printing. After printing, the electronics needed sintering so that we could stabilize their mechanical properties and their geometry. And that was very important to study the sintering time, the sintering temperatures to achieve good dimensional stability and be ready for injection molding. After that, we combined what we had done, so what we done on a mold insert, into a mold base that we use for some injection molding experiments. And finally, what we were checking was that we are able to transfer some of these printed traces onto a plastic part, and we're interested in checking the interaction between the printed traces and the polymer system and make sure that there's no porosity, that the morphology of it, the interface is completely full, and so we're not introducing any defects into those plastic parts.
So now we're going to focus a little bit on what some of the electronic packaging looks like in the electronics. And the next slide, we're going to show cross-sectional analysis of this A10 central processor. So if we look at that, you know, we cut a cross section and we polish it so that we can look at all the different layers inside that square chip. That's actually a completely enclosed, what is called in the industry, a package. And if you cross section that, you can see that there's several different key elements. One is there's a memory chip that's on top of that. And then here in this sort of corner over here is the A10 processor chip. And then on the bottom here is the high density interconnect. That's what HDI stands for. And then it's not shown in this figure, but on the backside of this board, then we have more packages built up on the backside. So let's just go through and I'll point out a few places where polymers are used. So let's start at the top, the stacked memory. There's a mold compound on the top here, which is epoxy. This is the memory chip right here. And then there's these circuit layers that are a combination of epoxy and cyanate esters. And I'll talk about more detail about the chemistry of this layer later on. And then underneath these solder balls here is an epoxy underfill. Right? So this top layer, this stacked memory, is bonded down to this so it can communicate with the A10 chip through a solder ball and these solder connections. And then the A10 chip is also encapsulated by an epoxy mold compound. But you can see there's all these little circuit lines here, and that's a layer called a redistribution layer, where the electrical signals come off of the chip and they get redistributed out. And in this case, they go out to this pad, and then that goes up so that the signal can talk to the memory.
So let me talk about the material requirement for the reliable connectivity. So when we talk about the 5G, the 5G use two different bands. One is sub-6 gigahertz, and then the other one is a millimeter wave. And to my understanding, the Asia more focused on the sub-6 gigahertz, and then the North America and the Europe more focused on the millimeter wave. It is probably because of infrastructure readiness. For example, North America and Europe, they have better infrastructure than maybe Asia. But however, the limitation for this high frequency is the high signal loss. For example, when this high frequency signal passing through the building in the city, then pretty much the majority of the signal may be disappeared. So this technology can be considered as short range communication. So this is some dilemma here. So in order to improve this short range communication, so there are a lot of technical challenges to realize this reliable connectivity. So I listed out these technical challenges here. And the first thing is we have the minimizing the signal loss. So the material point of view, this signal loss can be improved by low decay material or ultra low DF material here.
So the flexible hybrid electronics, I always say that the flexible part is really obvious. We print on flexible substrates. The hybrid's not so clear. What that refers to is we get thin flexible silicon die and we directly attach those. If you saw that one of the previous presentations, he was talking about flip chip. We're doing flip chip attached directly onto the printed circuit. And I'll show you how that's done. When we do all of this, we wind up with a new class of electronics that's flexible, stretchable, conformable, transparent, biocompatible, and lightweight. This is a quick cartoon to show you some of the building blocks that we'll talk about as we go here. Things, if you start at the right, things like printed or flexible battery integration. Printed antennas you heard about earlier in a number of different talks. And you'll see an example of that. We, of course, print the conductors, and we do apply discrete component attachments. We attach these die, in many cases a microcontroller. We can do printed passes. We can encapsulate or overmold the entire device. We do vias. We print on both sides of these substrates. We can do microfluidic structures, which we've done for some medical devices. We can do bonded or printed sensors, and we can use biocompatible adhesives or textile integration.
Mentioning. So speaking about flame retardants, what are the sustainable choices of flame retardants? Many of you will automatically say, well, non-halogen seem to be good, but new studies and regulatory actions suggest that they don't have the automatic safe solutions that everyone wants. So yeah, there are multiple reviews going on, but just to cite EPA, the two priority chemicals that are currently being reviewed and used in flame retardant application. One is phosphorus-based, one is bromine-based. So we think that the direction will be towards polymeric, reactive, or safer inorganic materials, and it will be regardless of halogen versus non-halogen chemistry. Will continue to be role for safer additive molecules, mostly larger, with complete set of EHS data. Why polymeric? Well, they have low water solubility. They don't present any leaching or migration issues. And because of high molecular weight, there's no penetration of living tissue, no potential for bioaccumulations, and with that, low toxicity. They're not included in any regulatory actions or reviews, and they are recognized as a sustainable solution. You have that conclusion from EPA that there is an exceedingly low probability that exposure to high molecular water-insoluble polymers as a class will result in any risk or injury to human health or environment.
So this is giving you kind of a very quick overview of our development process. The first thing we do is we've looked at designing our own monomers. As these properties get more and more difficult to meet, having only commercial monomers is probably not enough. So we have a subgroup within our team that works on developing new in-house monomers, and taking those with the commercial monomers, we have quite a large set of compositions that we can achieve. Once these are synthesized, the resulting film from this polyamic acid is casted, and the film is isolated and fully characterized. The polymer structure can be anywhere between linear or branch type structure or random copolymers, block copolymers, anything that you would envision a polymer chemist would think of. And once we get properties that are of interest, then we are starting to sample to customers. This is a very important step. As you would expect, customer engagement and feedback is crucial at really developing the next generation or improving properties that meet all the CTQs that a customer would require. And finally, once we pick a polymer that meets what we need, the next step is the scale up. And that is not trivial. Scale up from what we do in the lab, from grams to kilograms, is a very important work stream that we devote quite a lot of the time.